Okay, Assalamualaikum warahmatullahi wabarakatuh. Again, today we're going to discuss about the chapter 3. Okay, actually this chapter is quite heavy. Supposedly that we conduct this in 2 weeks. Okay, so that's why I'm telling you guys that the submission will be postponed for another week. So today we're going to discuss around half of the content first. Okay, and let's take a look at the question that we are going to discuss for today. So, okay, we start with this one, week 3 and 4 supposedly. Okay, chapter 3, digital logic and digital system. So you guys are familiar with the digital logic and digital system before, I guess, but some of you haven't. So digital logic and digital system is more like electronic circuits and everything, but actually it's much more simpler than electronic circuits. Okay, so this one is just when you have input and output of 1 and 0, you try to you have input of 1 and or 0, and then you try to guess the output based on the design of the components here. Okay, so let's start with the 3.1 here. Okay, so this one, okay, let's guess what kind of component they are. So this one is basically an N, okay, and circuit, and this one is NAND. Okay, you need to remember, okay, something that the straight one is N, the curved one is O. Okay, so N basically they representing times, or they're representing plus. Multiplication is N, okay, and or representing is plus, okay, sub addition. So this one is or, this one is no. Okay, this one is not, and this one is XOR. Okay, so here in this case, okay, if you look at, okay, NOR, NAND. Why do we need NOR and NAND when you have N and OR and NOT? Okay, basically this one, there is this NOR and NAND because they are created as one component. Okay, it's not that we can split them into two, but actually we can develop them as one, so that's why they have it as NAND. So NAND is basically the combination of AND and NOT. Okay, AND and NOT. So here they come into AND first and then they exit as NOT. So here is here. So actually the result first is 0 and then go 0 and 1. So at the end is 1. So it's not going to NOT first and then end up as AND. It's going in as AND and going out as NOT. Okay. So here is the names of the components that you have, okay, for the digital logics, okay, for the fundamental of digital logics. So let's guess what kind of output do we have. Okay, so now we have two inputs. So two inputs, usually they represent numbers from 0 until 3. Okay, you see 0, 0 is 0, 0, 1 is 1, 1, 0 is 2, 1, 1 is 3. So 0 until 3. So let's guess what kind of output do you have. Okay, here. Okay, what kind of output do you have? Okay, so I need to change the font a little bit. Okay. So 0 and 0, you look at this one is what? AND or OR? So this one is OR. Okay, basically OR. So OR, okay, 0 and 0, they're representing plus. So when representing plus, 0 plus 0 is basically 0. Okay, and then down here, okay, 0 and 1 representing 1. Okay, 1 plus 0 is 1. 1 and 1. 1 plus 1 is 1. So it's high. Everything is high. Okay, so you have 1 plus 1 is 1. Okay. Okay, so now we have n. So n is basically multiplication. Okay, so a and b, let's try. A multiplied with b, 0 multiplied with 0 is 0. 0 multiplied with 1 is 0. Okay, 0 multiplied 1 is 0. 1 multiplied with 1 is 1. Okay, so this one KIV this one first. Let's move on to the bottom one. Okay, so this one, next one is what we call uh, a NOR gate. Okay, so a NOR gate. So how exactly do you determine the output of a NOR gate? You have the output of an OR gate up here. So basically it's an opposite. So the 0 become 1 and the 1 becomes 0. Okay, the 1 becomes 0. Okay, so this is it. And the AND gate, okay, and the NAND gate. This one is a NAND gate. So you have for NAND gate, so same thing. You have for AND gate, so the 0 become 1 and the 1 become 0. Okay, so next one is an XOR gate. Okay, you have here XOR gate. So the difference between OR and XOR gate is simple. Okay, last one where you have 1 and 1, both is 1. Okay, the both is 1 actually is, when you put both is 1, the output is 0. Okay, so this one is usually used when you add, when you want to create a circuit for addition. Okay, 1 plus 1 is 1, 0, right? So there are 0 down and 1 going to up next. So this one is where we use XOR. Okay, so and then we have this one, okay, what you call it, NXOR. Okay, so this one is the opposite of what you have here. 1, 0, 0, and 1. Okay, so this is the answer for this circuit. Okay, next one where you have N. Okay, so this N is a little bit different than the previous N. Okay, so here if you see comparing this to NAND, okay, so this one not come first and then it goes to N. And this, in case of NAND, N come first and goes to not. This one not come first and goes to N. So look at the result here. Okay, 0 and 0 for input. So means that when 0 is coming in and 0 coming in from B as well, so they will change into 1 first. So here is 1 and 1, and the result will be 1 times 1 and it become 1. Okay, and next one is 1 and 0. 1 times 0 is 0. Next one is 1 times 0 is 0. And next one is 0 times 0 is 0. So basically, this one is different than NAND. Okay, this one is basically the opposite direction of N. Okay, you see that 1, 1 becomes 1. Here is 0, 0 become 1. Okay, so this is where you have the difference. And then for OR, okay, the same case for the N. Okay, so 0, 0, 0 plus 0 and 0 here become 1 and 1. 1 plus 1 is 1. Okay, so here 1 plus 1 plus 0 is 1. 1 plus 0 plus 1 is 1. And 0 plus 0 is 0. So you compare this one with the results of OR. Okay, so it's the opposite of the one on the top. Okay, so and then finally you have a NOT gate. Okay, so this is basically the same NOT gate. Okay, just the symbol is different. So in this case, okay, 0 become 1 and 1 become 0. Okay, just like that. Okay, So please finish up this exercise later on, okay, so that you can submit them properly, okay. So try to finish this part, these few parts this week, okay, up until 3.3 that I will show you later, okay. And then next week will be a little bit difficult for you to do, actually, to understand. So let's move on, okay. So now is to understand the truth table and Boolean algebra, okay. So in this case, okay, usually I mentioned that during the class you have three things: the Boolean algebra, truth table, and also digital circuit. And sometimes I will give, for example, in your assessment, either one first and try to guess the other two. So in this case, I gave you, okay, this one, okay, this one is what do you call it, a digital circuit, and here is the result that you have to guess, okay, the truth table that you have to guess, and here is the Boolean algebra for this circuit. So in this case, okay, let's try and build the truth table first. Okay, let's try and build the truth table first. Okay, so here on the left is 1. And we start with 0. Okay, start with 0 first. 0, 0, 0. Okay, and then you have 0, 0, 1, and then 0, 1, 0, and 0, 1, 1, and 1, 0, 0, and wait, 1, 0, 0. Why is it running away? 1, 0, 0, 0, 1, 0, 1. They automate the spacing here, kind of annoying. Okay, 1, 1, 1, 0, 1, 1, 1. Okay. Astaghfirullah. Okay. 1, 0, 0, 1, 1, 0. Okay. Supposedly this one should fit. Okay, so let me give it a little bit space. Too large. Okay, let's just make it a little bit, okay, something like this. Okay, so you have 1, 2, 3, 4, 5, 6, 7, 7 inputs. So you have from 0, 1, 2, 3, 4, 5, 6, 7. Okay, So let's guess the output here. Okay, from the top. Okay, start with 0, 0, 0. Okay, let's shrink this table so that it fits. Cannot. So I can fill in here. So let's just fill it here. Okay, 0, 0, 0, 1, 0, 0, 0, 0, 1, 0, 1, 1, 1, and 0, 1, 0, 0, 1. Oh, not enough. 1, 2, 0, 1, 2, 3, 4, 5, 6. Oh, we have another one. Okay, we missed another one. So let's. That's why it didn't fit. 0 and another one. So at the bottom. Okay, so this one is 1, 1, 1. Okay, so let's take a look at the output here. Okay, so in this case, okay, I would like you guys to write something like what I do here. Okay, so let's take a look at the output here first. Okay, at this one here. If you have a circuit, okay, write the input and output first. So the input here is X and Y. Okay, okay, on the top here, X and Y. So here, and then at the bottom here is, okay, you see that this one is from Y. Okay, and this one is from Z entering not. So this one is Z bar. So let's need to put in your equation. Okay, so this one is Z bar. Okay. Right. So I have to make it separate. This one is Z bar, and on top here is Y. Okay, so why Z bar is a Z entering a knot, so it becomes Z bar. Okay, and then down here at the bottom is X, Y, and Z. So here is X, Y, and Z. Okay. Okay. So this one is Z bar. Okay, now next find out what is entering the next level here. So this one is a time, so basically this one is X, Y. X times Y. And then the middle one is Y times Z bar. Okay. And the third one is X, Y, Z. Coming in. Okay. So at the end, the results is X plus Y plus xyz. Okay, so because this is an or will add everything. Okay, and will times, okay, will multiply or will add. So this is the results of your f. And this one is the Boolean algebra. F is equal xy plus y z bar plus xyz. Okay, so in this case, you can see that you can simplify the result. Okay, like for example, okay, f equal, okay, so this one you can have xy with 1 plus z, like an algebra. Okay, you see, because this way we have this xy and xyz, 1 plus z, okay, plus, okay, yz bar. So this one, if you follow the rule inside my lecture, okay, if you follow the rule inside my lecture, okay, so you notice that z plus 1, any alphabet, any input plus 1, the result will always be 1. Okay, the result will always be 1. So this case, it's xy only, xy plus y z bar. Okay, so y z bar. So here, in this case again, you can even simplify it even further. Okay, equal xy, x, no, y, x plus z bar. Okay, so the final equation, the most simplified equation that you can get is f equal y x plus z bar. So this one will represent the same equation, the same circuit as this one. Okay, so firstly, let's fill in the truth table first. Okay, so here f equal y x z bar. So if y equal 1 as 0, x equals 0, z equals 0, so it's okay, every times y equals 0, the result will be 0. So you just write here, okay, 0. Okay, this one, because y equals 0, the result will always be 0. Okay, now write the 0 first. Okay, now every result, y result is 1. Okay, and if x is 1, z is either 1 or 0. Okay, the result will always be 1. So as long as x is 1, okay, x is 1, the result will always be 1. Okay, now when x is equal 0, z is 1, and y is 1. Okay, when z is 0, z will become, z bar is 1. So 1 plus 1 is 1. So in this case, here will become 1. Okay, when y equal 1, x equal 0, and z equal 1, okay, z will become 0 here. So 0 plus 0 is 0. So 0 times 1 is 0. So here will become 0. Okay, so this is the result of the truth table that you get here. Okay, so now this one is a more simplified circuit version, better than this one. So let's try and draw a new circuit here. You see, there are only one times and one add. So in this case, there is also one not here. In this case, you have 3 inputs. Okay, in case that let's insert a new text box here. Okay, you have 3 input x, y, and z. Okay, so you have 1 times, 1 not, and one addition. So you have 1 times. Okay, I like to use PowerPoint because PowerPoint have most of the shapes already available. So you have this or, okay, okay, and then you have one not. So not, you need to combine two things, the triangle and also a circle. Okay, so let's build it up first. Okay, when you build a circuit, you need to make sure you do the same thing that when you do calculation. You need to do the bracket one first. Okay, the bracket one is to the left. Okay, the more outer one will be to the right. So first, inside the bracket, you need to do the bar first. Okay, you have this bar. So z bar and z. Okay, z here. Okay, and then you need to do addition next. Okay, and then you need to do multiplication. Okay, so in this case, okay, let's draw some lines. Okay, so from here we'll go into here. So make sure you connect it properly. Okay, and then you have x. Okay, from x going to here. Okay, from z going to the north first. And finally from y going to top one. Okay, and then this one will be from here to here. Okay, so you see that this one is z becomes z bar. Okay, and then z bar you add with x, and then y will add the result from this x plus z bar here. And this will be the last answer. Okay. So this is the same circuit that can produce the circuit that can produce this truth table. Okay, this one is the same as the top one. Okay, if you see that this one use less component in terms of engineering the circuit. Okay, this circuit will cost less comparing to the top one. Okay. So that's why we need Boolean algebra. So when we have Boolean algebra, we can simplify the circuit, okay, to the most simplified form so that you can save the cost lah. Okay, save the cost and space of your electronics that you want to build later. Okay. Okay then. So let's go to the final question here. Okay, so in this case, you have a question. Okay, not a circuit, not truth table, or not Boolean algebra. So this one, okay, supposedly you need to understand Karnaugh map, but I haven't covered Karnaugh map yet. So let's just do the task here so that, okay, you can understand how Karnaugh map works later. Okay, so firstly, because we need to draw the truth table, so let's just copy from here. Okay, so you have three outputs A, B, C. We can change. Okay, A, B, and C. So this one is the border. Okay, let's just delete the box out here. Okay, so let's trace back, okay, in case everything to 0 first to avoid confusion. Okay, so let's read the question. Okay, so this one they want us to construct the truth table first. Okay, so here you have three conditions. A logic circuit has one output and three inputs. The circuit produces no output whenever the three inputs are 0, 1, 0, 1, 1, 0, and 1, 1, 1. So basically 0, 1, 0 is this one. Okay, let's just color shade it. 0, 1, 0, and 1, 1, 0 is this one. Color shade it again. And 1, 1, 1 is the bottom one. Okay, so during this input, okay, they say that the output will always be 0. So other than this, okay, the output is 1. So easy to understand, right? Okay, so next, okay, next is we draw a circuit. We draw a table, a small table lah, actually. And this table is 4 times 2. That's 3, 4. 4 times 2, okay. This one is for you to use Karnaugh map. Okay, design is normal design. No, just this one. Okay, so there's nothing here. Okay, so here you put C. Here is C bar. Here is C. C bar. So here is A. Okay, so here is A, B. A bar B. So here is A bar, B bar. It's so stressful. Not changing. Okay. Okay, good. Okay. So here in this case, what do you mean by ABC? So ABC means it's a 1, 1, 1. Okay. So A bar BC means a 0, 1, 1. Okay. So A bar B bar, so it's a 0, 0, 1. Okay. So let's try and here 0, 0, 1. 1, 1, 1 is 0. Okay. 1, 1, 0, okay, is 0. 0, 1, 1 is 1. 0, 1, 0 is 0. Here, A bar, B bar, here is 0, 0, 1 is 1. 0, 0, 0 is 1. Okay, here is 1, 0, 1. 1, 0, 1, 0, 1 is 1. 1, 0, 0 is 1. Okay. Okay. So in this case, okay, let's find out, okay, what kind of results that you can get. So you just need to group the ones. Okay, group the ones like what I did here. Okay, group this one. Okay, I group this one. Okay, so this is the first group, my first group. Okay, so you can group them according to 2, 4, 8, 16. Okay, so 1, 2, 4, 8, 16. Okay, 1 is there are no grouping involved lah. So in case you can group into 2, group into 2. In case you can group into 8, 4, you can group into 4. You can group into 8, you can group into 8. So in this case, we can group into 4, and you can even stack the group if possible. Okay, next one you can group into 2. Okay, so here is the second group. Okay, so this group, okay, based on the red group first. So the red group, in this case, okay, you draw the circuit first, the algebra first, F. F equal. So look at this one, the group. So the red group, A is bar, A is not bar, C is bar, C is not bar. So means that A is bar, whatever A is and whatever C is fine. But the most important thing is that B must be bar. So B must be bar. When B is bar, the result will be 1. So here you put in B bar. Okay. So next one, you look at the green one. So in this case, C is confirmed to be always 1, C. Okay. And then A need to be always with bar. Okay. And B, no matter whatever B is, okay, the result can be 1 when C is 1 and A is 0. So in this case, you can just put in A bar, okay, A bar and C. Okay, now you finish your most simplified circuit using the Karnoff map. So this is the most simplified circuit for your equation in case of this question. So let's draw the circuit. Okay, so you have 1 times and 1 add and 2 knots. Okay, 1 times and add. So here you need to do the one, the smaller one first. Okay, we need to do the times first. multiplication first, and then you insert the OR. Okay, and then you have, okay, here you have A, B, C. Okay, 3 inputs. So you need to do the multiply first. And in this case, you need to change A into a not first. Oops. Okay, and then you need to change B into a not as well. Okay, so AC, you need to add AC first, A bar C first. So here in this case, add this one, A bar. Okay, and then here is another one. And then here from B into the top. Okay, it's okay if you want to do it with arrow or without arrow. It's better to use without arrow. Okay, less confusing. Sometimes students tend to ask me, so why you use, sometimes you use arrow, sometimes you use without arrow. So either one is fine. Okay, but just to avoid you from confused, okay, so let's use without arrow. Okay, so this one, final one, just a small short version. Okay, so we finish your circuit. So this one is an easy example, okay, for you to use the design that I've shown you here. Okay, so based on this question, okay, please try to answer the task. Okay, I've given you the answer already, so please take a look at it and do it yourself. Later on, if you are not sure, you can refer back to this video. Okay, I will upload this video later on. Okay, so for those who haven't subscribed my channel, please do subscribe my channel. Okay, so easier when I update, I don't need to notify you, you'll get notification yourself. Okay, so please do subscribe my channel. Okay, thank you very much for the likes. Okay, I'll see you guys next time. Okay, I will upload more videos later on regarding this kind of map, and also some new exercise regarding application called Logisim. Okay, so which can help you understand how the logic circuit works later. Okay, so that's all for today. I see you guys on my next video, and hopefully I can meet you again next week on Monday. Okay, so that's all. Thank you. See you later. Bye.
Thank you, sir.
Thank
Thank
you,
you,
sir.
sir.
Thank you,
Thank you,
sir.
sir.
Thank you, sir.
Thank you,
Alright,
sir.
thank you, sir.
Okay,
Okay, thank
welcome.
you, sir.